Today we're going to talk about transformations of functions. So we're going to go through a handful of different functions and see what happens when we add, subtract, multiply, or divide those functions. So here we've got f of x equals x squared. So here's my x values, and if I square them, these are my y values, or my outputs. So negative 3 squared is 9, negative 2 squared is 4, negative 1 squared is 1, and so on. And that is right here in this dashed parabola. Okay, so that's f of x. G of x, and it says plot it on your calculator, but we're just going to go ahead and do this by hand here. So g of x is x squared minus 2. So negative 3 squared is 9, minus 2 is 7. Negative 2 squared is 4, minus 2 is 2. Negative 1 squared is 1, minus 2 is negative 1. 0 squared is 0, minus 2, negative 2. 1 squared is 1, minus 2 is negative 1. 2 squared is 4, minus 2 is 2. And 3 squared is 9, minus 2 is 7. So we're going to plot these points now. Here's my x's and my y's. So negative 3, 7, and that's not actually going to fit on here. Negative 2, 2. Negative 1, negative 1, negative 1. 0, negative 2. 1, negative 1. And 2, 2 is what will fit. So it looks like this. Okay, so what is this function type? F of x equals x squared. That is a square function. Does the change happen before or after the function? So this is the change, this minus 2. Everything shifted down 2 units. Did that happen before or after the function? Well, by order of operations, x squared minus 2, the squaring happens first. So that change happens after that function. What changed? It shifted down 2. So from this original function to the transformed function, it shifted down 2. Okay, if it were g of x equals x squared plus 2, what would have happened? Then it would have shifted up 2 instead of down 2. So if it was a plus 2 instead of a minus 2, it would have been shifting up 2. So how would you describe this movement? When something shifts, that's called a translation. When it shifts up or down, that is vertical. So I would describe this as a vertical translation. And write a general equation for this particular movement. That would be g of x equals f of x, which is our original function, plus some constant. If that constant is positive, it would shift up 2, like this. If that constant is negative, it shifts down 2. All right, so the next one, we start with this square function again, this parabola, and this time it's x minus 4 squared. So if x is negative 2, minus 4 is negative 6, squared is 36. Negative 1 minus 4 is negative 5, squared is 25. 0 minus 4 is negative 4, squared is 16. 1 minus 4 is negative 3, squared is 9. 2 minus 4 is negative 2, squared is 4. 3 minus 4 is 1, is negative 1, squared is 1. 4 minus 4 is 0, squared is 0. And 5 minus 4 is 1, squared is 1. Okay, so we're going to plot on here what will actually fit. I think that's pretty much from here down. So we've got the point 2, 4, 3, 1, 4, 0, and 5, 1. Okay, does the change here happen before or after the function? So the function was x squared, and here, because that minus 4 is inside of what's being squared, that change happens before the function. Okay, and what changed this time? It shifted right 4. Okay, now notice up here, we had a change happening after, and it shifted up or down. That's vertical. Here we've got a change happening before the function, and it shifts right. That is horizontal. And notice also it said minus 4, and we ended up shifting 4 to the right. If it said plus, we would have shifted to the left. So if it was x plus 2 squared, then we would have shifted left. And in this case, we would go left 2. Okay? If it were x minus 3 squared, we would shift right 3. How would you describe this transformation since it's moving left or right? This is a horizontal translation. And a general equation for this, g of x equals the original function plus a constant, but that is inside, so it's f of x, and I'm going to put minus c, because in this case it goes the opposite direction. So if c is a positive, it goes minus that positive, which means it goes left. If c is negative, then minus negative becomes a positive, and it shifts right. So that minus right there really means just go opposite the sign. What two movements would occur from the original graph if we've got this function? X minus 100 squared plus 25. So that minus 100 inside of that function means it's going to move right 100. And that plus 25 outside of the function means it is going to shift up 25. Okay, now this time we are multiplying by a 2 here. Okay, so we're doing the squaring and then multiplying by 2. So for x squared, here's your outputs. For 2 times x squared, we've got to square this and then multiply by 2. So that's 9 times 2 is 18. Negative 2 squared is 4 times 2 is 8. Negative 1 squared is 1 times 2 is 2. 0 squared is 0 times 2 is 0. 1 squared is 1 times 2. 2 squared is 4 times 2. 3 squared is 9 times 2. Right, so we will graph the ones that we can fit. So we've got 0, 0, 1, 2, and negative 1, 2. Negative 2, 8, and 2, 8. Some people would look at this graph and say, hey, it got skinnier, but no, it didn't get skinnier. What happened was it got taller. These outputs right here moved up. And these two outputs moved up. Okay, so what's happening is each output is getting taller. Now, does this change happen before or after the function? By order of operations, the squaring happens before the multiplying. So the change happens after the squaring function. Okay, what changed? The y values doubled. Because we multiplied by 2. Okay? So what that really means then is the output was stretched. Okay? What would have happened if it was 1/2 times x squared instead? Then it would have, instead of stretching and becoming twice as tall, all these outputs would have been cut in half, so it would have been twice as short. That's still a type of dilation. Anytime you stretch, that's a type of dilation. So this right here was a vertical dilation by 2. If it was by half, then it would be a vertical dilation. I'm going to abbreviate here, vertical dilation by 1/2. How would you describe this movement? It's a vertical dilation. And a general equation for this, g of x is some constant times f of x. So what movements happen in this equation? G of x equals 4 times x plus 10 squared. So this plus 10 is happening before the squaring function, which means it shifts it right or left. And when you're shifting right or left, it's opposite the sign, so it's going to shift left by 10. And then this right here is going to stretch it 4 times as tall. So it's going to have a vertical dilation by 4. So it's going to become 4 times as tall. So it'll shift left 10, and it'll become 4 times as tall. All the outputs will be multiplied by 4. I notice this time we're multiplying again, but this time it is multiplying inside of this squaring. So it happens before the function. Okay, so the change happens before the function. Then the function of squaring takes place. Okay, so what is 1/3 of -3 and then squared? So 1/3 of -3 is -1, and you square that and you get 1. Okay, if you take 1/3 of -2 and you square it, you're going to get 0.4. Okay, so there's going to be some decimals in here that we won't really be able to graph very easily. If you take 1/3 of -1 and square it, you're going to get 0.1. Okay, and then 0, 1/3 of 0 is 0, squared is 0. And then it's going to be symmetric on the other side. Okay, so the ones that we can graph are 0, 0, -3, 1, and 3, 1. So it's going to look about like that. So this time, instead of getting taller or shorter, it's actually getting wider. These outputs right here move wider. Okay, so what changed? What changed is that it actually takes 3 times the input to get the same output. So notice here, I had a -1 and got an output of 1. But then, after my g of x, where I'm multiplying by 1/3 inside the function, it takes a -3 to get a 1. So it took 3 times the input to get the same output. Okay, so it's the input that is stretched. So the input was stretched 3 times. It took 3 times the input to get the same output. So what if the graph was 2 times x squared? Okay, then I would have another stretch, which is a dilation. Okay, so this is a dilation. This time it happens to be horizontal. It's moving in or out rather than up or down. So I would have a horizontal dilation. But notice here I had 1/3 as my multiplier, and it stretched 3 times. Here if I have a 2, it's going to be horizontal dilation by 1/2. So that would actually move in halfway back to the axis. Okay, so when it's a horizontal dilation, it turns out to be by the reciprocal of whatever we're multiplying by. So how would you describe this type of movement? This is a horizontal dilation. Not really sure how I got that extra little piece right in there, so I'll fix that. Okay, and a general equation for this, g of x is the reciprocal, so it's f of the reciprocal of a constant times x. So what two movements are happening here? We've got a horizontal dilation because it's multiplying inside of that function. And it's by the reciprocal of this, so it's a horizontal dilation by 2. And then that plus 10 after means that it's going up by 10. So I'll write the word shift. We are going to shift up 10 units. All right, so here's a new function. It's a square root function, and it graphs like this. And the other graph would be the opposite of the square root of x. Okay? So we are multiplying outside of the function by a negative. And that would cause a vertical reflection, which means it's going to flip over the x-axis. So all of these points are going to flip over the x-axis. A general equation for that is g of x equals the opposite of f of x. Well, what if that negative is inside? And when that negative is outside, anything that ever happens outside is vertical. When that negative is inside, now we're looking at something that is horizontal. So this is going to be a horizontal reflection. Which means it's flipping over the y-axis. So when we reflect that over the y-axis, all of these coordinates are going to flip this way. So it's going to look like this. A general equation for that is g of x equals, and since this negative is inside, it's going to be f of the opposite of x. All right, so now we've got f of x equals x squared minus 1. That's what's right here. It's a parabola shifted down 1 unit. What if we did the absolute value of x squared minus 1? How would you describe that? So what absolute value does is it takes all of your negative outputs and makes them positive. Okay, so if an output is negative 3, the absolute value is positive 3. So all negative outputs, which are negative y values, flip over the x-axis. They become positive outputs. Okay, so right here, I've got a set of negative outputs, and what's going to happen is they're going to flip over and become positive outputs. So when I do the absolute value of x squared minus 1, it looks like this. So just all these negative outputs, absolute value doesn't allow them, so they flip over and become positive outputs. A general equation for that is g of x is the absolute value of f of x. That absolute value is outside the entire original function. What if that absolute value is inside the original function? Okay, this one's going to look a little bit more odd, but what actually happens is this positive part of the domain, so this is a parabola shifted 1 to the right. The positive part of this domain is going to stay, but it's also going to reflect over the y-axis. So the graph would look like that. Okay, so the positive domain is symmetric about the y-axis. So the positive domain stays and it reflects over the y-axis. And a general equation for this is g of x equals f of the absolute value of x.